Section 3.7 on improper integrals. So whenever we have been evaluating an integral up to this point in time, a definite integral, to find the area under a curve, for instance, we have an upper limit and a lower limit of a and b, and they are definite points. But what happens sometimes is if we have one of our limits is approaching infinity. So the first type of problem is integrating over an infinite interval. So as an example, let's look at the definition down here. So if we have an integral where the upper boundary is infinity, okay, so the upper boundary here is not b, but it is infinity. Okay, so essentially that means there's no upper bound. Well, that would seem like, well, if there's no upper bound, there's going to be an infinite area. That would kind of be a logical conclusion, and that may be true. There may be an infinite area underneath the curve. However, there could be an actual area, and it depends on how quickly the curve converges. And so that's what this is all about, is determining whether an integral converges or diverges, and we do that by finding the limit. So we take the limit, we replace the upper bound of infinity with t, and we take the limit as t approaches infinity. And that's what they're trying to show you up here. So we have t moving closer and closer to infinity. So t right here is, fairly close to a, and now t is getting a little bit further from a, getting further from a, and so it's going to get further and further and further and further and further from a. Then t will be out here, then out here, then out here. So t is approaching infinity, all right? And so we want to find the limit of this integral. So we're going to integrate a function just like we always do, but then we have to add one more step, which is where we find the limit of that integral as t approaches infinity. So let's do the first example, which is similar to that. So here we have the function 1 over x. And so we want to determine whether the area between the function and the x-axis over the interval is finite or infinite. So we set up the integral. We have the upper bound is infinity, right? So we're approaching infinity. This is going out infinitely far here. So the t is moving out further and further and further. So we remove the infinity and we put in a t, and then we find the limit as t approaches infinity. So that upper bound is getting infinitely large. So our first task is to simply evaluate the integral. Well, the integral of 1 over x dx, that's a pretty simple one. It's the log of the absolute value of x. So we're evaluating the log of the absolute value of x from t to 1. So substituting t in, we get the log of t. Substituting in 1, we get 0. The log of 1 is equal to 0. So that just becomes 0. All right, now here's the part that's the new part. This is the part that is going to require a little bit of intuition. It's going to require you to remember a little bit about finding limits and just kind of some reasoning. So what is happening so this is just 0. That's not going to change, but we want to look at what's happening here because that's where the t is. As t is approaching infinity, this means we're getting the log of t is getting larger and larger and larger and larger. Well, the easiest way to think about that is to know what the logarithm function looks like. Logarithm function looks something like this. So what happens as t is going out further and further and further and further? So t, it's going towards infinity. It's getting larger and larger. As t approaches infinity, t is getting infinitely large. Okay, t is getting bigger and bigger and bigger. So this whole thing is getting bigger and bigger and bigger because the graph is going upwards. Graph is going upwards. And so this whole thing is infinity. So what we have here, get rid of some of this, is this is getting infinitely large minus 0. Well, infinity minus 0 is simply infinity, and it's positive infinity. So that means our answer, our limit, is positive infinity. That means the area is infinitely large. We say whenever the limit is infinity, we say that the integral diverges. So the area is infinite, and this integral is diverging. Most of your homework problems are going to be pretty simple. You just have to pick diverges or converges, but you need to figure it out. Please don't just pick one, see that it's the wrong answer, and then just pick the other one. Make sure that you go through and reason out why it diverges or converges. Okay, let's go back and look at the second case. So what happens if the lower bound is infinity? Now, if the lower bound is approaching infinity, so if we look, that would mean that the lower bound, so we have a function, let's say it's going out this way. Well, that's actually negative infinity out that direction, right? So with the lower bound is going to be infinite, it's going to have to be a negative infinity. So the lower bound is going out to the left towards negative infinity, infinitely far. That's why that's a negative. And so we do the same thing. We replace the negative infinity with t, and then we find the limit as t approaches negative infinity. And again, if the limit exists, the improper integral is said to converge. If the limit does not exist, then the improper integral says it diverges. So let's go to example number 2. So the lower bound here is negative infinity. So what I'm going to do is I'm going to set up the integral. I replace the negative infinity with t, and I take the limit as t approaches negative infinity. All right, so just forget about the limit part. Let's evaluate this integral. Well, that's just a u substitution. Let u be equal to 5 minus 10x. du is negative 10x. dx is equal to du divided by negative 10. So you end up with the integral of, 1 over u times du over a negative 10, which is a negative 1/10 the integral of du over u, which is going to be the log rule. All right. So that's what we have. So I go through that here and then to here, and then replacing the u with 5 minus 10x, we end up with this. Okay. So now we want to evaluate our logarithm at 0 and at t. So first of all, when we replace x with 0, we simply get the log of 5. And when we replace x with 10, I didn't write that here, but we end up with, let me erase some stuff. When we replace that, we get the log of the absolute value of 5 minus 10t. Now, t is approaching negative infinity. All right. So as t is approaching negative infinity, here's the way I think about it. I get negative 10. I just do substitute. I just put negative infinity in there. All right. So we have the log of 5 minus negative 10 times negative infinity. Well, what's 10 times infinity? 10 times infinity is infinity, right? And a negative times a negative is a positive. So we end up with 5 plus infinity. This is the log of 5 plus infinity. Well, what is 5 plus infinity? It's infinity. So that just becomes the log of infinity. And so what is the log of something that is getting infinitely large? It's infinity, just like we did in the last problem. So this second term here is becoming infinitely large. This whole term is approaching infinity. If anything in your problem is approaching infinity, most likely the whole thing is going to be getting infinitely large. So the log of 5 minus infinity, Yeah, so I already did that. So the whole thing is just diverging. It's approaching infinity, and it is diverging once again. So we have two problems, both of which are diverging. So you have to recall a little bit about finding limits, and some of this sometimes is intuitive reasoning, I call it. Forget like memorizing limit rules and stuff like that. Just kind of stick infinity in for t and ask yourself what is happening as this gets infinitely large or infinitely small. Sometimes it helps to look at the graph. What is the graph doing? Or just kind of reason it through. All right, the third case, which we have right here, is what happens if the upper bound and the lower bound are both infinite. So if we have a function, and in the negative direction, this function is, let's say it's a function that looks like this, and we're going towards negative infinity over here and positive infinity over here. Well, we want to know if this function is converging to something or if it's diverging as it approaches infinity in negative infinity. So what we're doing is we're going to break it up into two problems. We break it up into the first integral, which is just like the second problem that we did up here, where the lower bound is approaching negative infinity, and then just select an upper bound, something simple like 0. 0 is usually a nice number to use, unless the function's undefined at that point, which it's not right now. And then we're going to add to it, we're going to do where the upper bound is infinity. So we have to break it up into two separate problems, which is basically a combination of the first two problems that we did. So it's a little bit more work. And that will be like example number 3. So in example number 4, I'll come back and do 3 again here in a minute. In example number 4, the lower bound is approaching negative infinity. The upper bound is approaching positive infinity. And so I break that up into two integrals. Here's the first one, and here is the second one. In the first one, the lower bound is replaced with a t, and we're taking the limit as t approaches negative infinity. In the second one, the upper bound, infinity is replaced with a t, and we're finding the limit as t approaches positive infinity. All right, so now when you actually integrate these, you only have to do it once because this integral is the same as this integral. So once you find the antiderivative, you don't have to do it twice. So this is another u sub. The actual integrating in these problems probably won't be too difficult because the emphasis is on finding the limits. So u is equal to negative x squared. So we have an e to the u type problem. Du is negative 2x dx, or dx is equal to du divided by negative 2x. So what we have here, which I didn't write because you should be able to do this by now, we have 7x e to the u times du over negative 2x. Well, that x cancels with that x. This 7 and negative 2 come out here, negative 7, 2, times the integral of e to the u du. And so the integral of e to the u du is e to the u. So we end up with negative 7 halves e to the u, which replacing the u, I'm going backwards now, is negative 7 halves e to the negative x squared. We're going to the left here. And so that's what we've got right here and right there. But again, you should be able to do that u substitution with no problem. All right, so now it comes time to evaluate these integrals. So we're going to replace the negative x squared, or the x, with 0. So we have negative 0 squared is just 0. And then we're replacing it with t. So we have a negative t squared. Then over here, we're replacing it with t again, and then with 0 again. So let's go through and figure out what each of these is equal to. All right, so e to the 0 is 1. Anything to the 0 is 1, so negative 7 halves times e to the 0 is just negative 7 halves. And that's going to be the same thing over here. Negative 7 halves times e to the 0 is negative 7 halves, and we have a minus negative 7 halves, so that becomes plus 7 halves. Now this part, if t is approaching, what is t approaching? Negative infinity. Well, we're squaring t. So negative infinity, the way I like to think of it is, what if I take negative infinity and I square it? What's negative infinity times a negative infinity? Well, negative times negative is a positive. Infinity times infinity is infinity, right? So we end up with the t squared is negative infinity squared is infinity. Now here's the tricky part. Listen carefully. Okay, we have negative t squared. Let me find some room to do that right over here. So we have e to the negative infinity squared when we replace the x with negative infinity. Okay. So negative infinity squared is infinity. So now we have e to the negative infinity. So what is e to the negative infinity? It is 0. How do I know that? Well, what does the function of e to the negative, what is the function of e to the negative infinity is as e is approaching negative infinity. This is what the function e to the x looks like. This is the function e to the x. As x is approaching negative infinity, this direction, it's getting closer and closer to 0. This is just a function. This is a characteristic of the function of e to the x, all right? That's my function e to the x. So it's approaching negative infinity. And so, I mean, it's approaching 0. Getting closer and closer and closer to the x-axis. So e to the negative infinity is equal to 0. So that means that this term becomes 0, and the same thing is going to happen over here. That's 0. So we have a negative 7 halves plus 7 halves is 0. Well, 0 is a number, okay? It's not infinity. It's a number. And so whenever the limit, so we've taken the limit, our limit is now 0, which means that this converges. So this might seem a little bit confusing, like a lot of the problems in this whole section. It takes time to go through these. Take your time to go through these problems numerous times if you need to. Go through these problems in my notes on your own, watch my video, and eventually it will kind of make sense to you. But you have to recall some things that you've done in the distance past, like Calc 1. All right, let's go back and do this last problem here. I gotta get rid of all this now. All right, in this problem, state whether the interval is convergent or divergent. This is like the first one that we did. The upper bound is approaching infinity. So we're going to take the limit as t approaches positive infinity, and we change the upper bound to t. So this is a u substitution problem. U is simply 9x. Du is equal to negative 9 dx. Dx is equal to du divided by negative 9. So you're going to make the integral of e to the u times du divided by negative 9. So that gives me a negative 1/9 times e to the u du, and the antiderivative of e to the u is e to the u, so it's a negative 1/9 e to the u, which is negative 1/9 e to the negative 9x. So that's what we get here. And now we evaluate that from t. So taking out the x, putting in t, and then taking out the x and putting in 2, all right, we end up with e to the negative 9t. So again, with these, because the exponents are negative, here's another way I like to think about that. All right, let's take, I'm going to erase all this over here now. So here's another little trick that you can do with these exponentials to a negative. E to the negative 9t is equal to 1 over e to the positive 9t. All right, so t is getting infinitely large. T is getting infinitely large, which means 9t is getting infinitely large. So the exponent is getting infinitely large. So basically what is happening is the exponent is approaching infinity. All right? T is infinity. 9 times infinity is infinity. So we have 1 over e to the infinity. Well, as e to the infinity is getting infinitely large, because again, remember what the graph of e looks like. It looks like this. It's getting infinitely large. So as the denominator is getting infinitely large, the entire fraction is approaching 0. As the denominator of a fraction gets larger and larger and larger, and the numerator stays the same, that entire fraction approaches 0. So what's happening is this term right here is approaching 0. So what we have is we have negative 1/9 times 0 minus, now what's happening? Well, 1 over e to the 18th times 1 over e to the 18. So this is 0, so we just multiply this times this to get this, and that's our answer. That is our limit. The limit is 1 over 9e to the 18. And so because that is a number and not infinity, it converges. So this particular integral converges. All right, I hope this was helpful. We've got one more video to go, and then we are done with this particular chapter.